In this chapter, we will be using calculus as a tool in curve sketching. In this video, we'll be sketching the graph of y equals x to the 2/3.
Right. Now, in this case right here, we're going to take a look at f of x equals x to the 2/3. We're going to sketch this. It seems pretty simple, and it is actually pretty simple. Its behavior is actually quite nice here, but it does have something that's worth looking at. Let's take a quick look at the domain. Okay, that's our first step here. Notice that there is no value of x you can plug in there that you can't take the cube root of. Okay, you can take the cube roots of negatives, that's not a problem. You can take the cube root of 0, it's not a problem. And every time you do that, you'll be able to square that result. So there's no issue here. It's going to be x as an element of the reals. 2, let's take a look at the intercepts. Well, let's look at the y-intercept first because it's easy. Plug in a 0. 0 to the 2/3 is going to be 0. So I know that it's going through the origin. Whoops, can't see that. I know it's going through the origin, which actually answers my x-intercept as well. But let's just take a quick look. If I let y go to 0 here, x to the 2/3, I would take both sides to the 3/2. But again, 0 to the 3/2 is just 0, which takes me right back up to 0, 0 as my intercept. Let's take a quick look at symmetry. If I plug in negative x into this, I'm going to get negative x to the 2/3. The cube root preserves the negative, but the square gets rid of it, and so the result is going to be x to the 2/3, which means, therefore, this is even. Okay? Or symmetric. Okay, it's going to be symmetric about the line x is equal to 0. Awesome. And again, not that we're going to use that necessarily to help us graph this, but we can use it as kind of a reference. As long as our graph is symmetric, then we know that we're on the right track here. 4, asymptotes. Well, it's not irrational, so there are none, I should say. All right, 5 here. We're going to look at intervals of increase and decrease here. So that means we're going to take the first derivative, and that's actually really quite easy. It's just going to be 2/3 x to the negative 1/3. Now, we are interested in looking for the critical numbers of the function here, which occur when the first derivative is either 0 or undefined. Now, bear in mind, this is the same as 2 over 3 multiplied by the cube root of x. Only the numerator will determine where this goes to 0, and so you can see right away it won't. But the denominator is going to go to 0 when x is 0. So that means, okay, it's going to be undefined there, but that is still in the domain of the original function. So this is a critical number, which means that could be a max or a min. So let's just take a quick look at the number line. If we plug 0 in here, if you take a negative number and plug that in, the cube root of a negative number is negative, which means the whole thing here is going to be negative. Cube root of a positive will be positive, which means the whole thing is going to be positive. So my first derivative is, let's say, negative from negative infinity up to 0, which means my function is decreasing from negative infinity to 0, but including the 0. Okay? Because although the first derivative is undefined there, the original function is defined there. So I can include that. The first derivative is positive on the interval from 0 out to infinity, which means the function is increasing from 0 out to infinity. So for 6 here, our max min here, well, I know this is going to be a min at 0, and we've already established that that's going to be 0, 0. Now, based on what we're seeing right here, I would argue that that's going to be an absolute min. Okay? But for right now, we can simply say that it's a relative min. We'll know for sure whether it's an absolute once we go a little bit further on here. 7, concavity, okay, which means we have to take the second derivative. So I'm just going to use this one up here. So the second derivative is going to equal negative 2/9 x to the negative 4/3. And when I write that, with positive exponents, that is going to be the cube root of x to the fourth here. Now, the critical numbers of the first derivative will occur where the second derivative is 0 or undefined. Again, it can't go to 0 because there's no variable in the numerator. So I'm interested in where it's undefined, and I know it's going to be undefined now at 0. And I know that because once an undefined shows up at a specific value in a derivative, every subsequent derivative will also have that same undefined value. So I knew that was going to happen here. So I knew that it was going to be undefined there. And because this is in the domain of the function, this is a critical number of the first derivative. So let's take a look what's going on here. Here's 0. If you pick a negative number to the fourth power, that's going to be positive. Cube root of a positive is positive. But I got a negative 2 in the numerator, so that's going to be negative right there. If you pick a positive number and take it to the fourth power, it becomes positive. And again, that negative there is going to make it negative. So what's happening here is this thing is actually going to be, now watch this, the second derivative is going to be negative, less than 0, from negative infinity up to 0, and 0 out to infinity. It's negative basically everywhere except at 0 where it's undefined. But that means that this thing is going to be concave down on the interval from negative infinity out to infinity. Now the reason I go right over 0 here is because normally I would include the 0 as an endpoint to those two intervals because the original function is defined there. But in this case, because that 0 is the endpoint of a decreasing sequence and now the beginning point of a decreasing sequence, or sorry, I did not mean decreasing, I mean concave down. It's the endpoint of a concave down sequence and or interval and the beginning point of a concave down interval. I'm kind of concave right through it. Concave down right through it here. So what does that mean? Well, that means over here, for 8, we don't have a point of inflection. We've got a cusp. That's the cusp at 0, 0. So what does this graph look like? Well, we know 0, 0 is important. In fact, it's the only really significant point that jumped out at us. In terms of my first derivative, I know that I'm decreasing here and increasing here. In terms of my concavity, I know it was concave down here, concave down here. Remember, I use the little sad faces to illustrate that. So it's going to be, oh, and sorry, by the way, one other thing here. I knew the first derivative went undefined at 0, so I know it's going to go vertical there. So the function's got to look something like this. Come down. So it comes down to this really, really sharp point right there. Decreasing concave down and then increasing concave down with a really sharp point right there. And that's what it looks like when you got a cusp. And that's the sort of thing that you would expect to see in the algebra when you're working towards a cusp.